Hello everyone, welcome to Chem Analysis. In this video, I will solve previous year Organic Chemistry GATE 2019 question. From the first question, we can see that we have to tell about the number of dienes among this given diene which undergo Diels-Alder reaction with methyl acrylate. This is the dienophile. Now we know from the reaction of Diels-Alder that there is one diene and it reacts with a dienophile, and the diene reacting must be in cis orientation. That means among the given options, those dienes which are in cis orientation will take part in Diels-Alder reaction. Now for the first case, we can see it is a cis diene, so it will take part in Diels-Alder reaction. This will also take part, but it is trans diene, so it will not take part in Diels-Alder reaction. This will take part. This is also trans, so it will not take part, and this is cis, so it will undergo Diels-Alder reaction, and this is also cis, so this will also undergo Diels-Alder reaction. So we can see that the 5 diene is taking part in Diels-Alder reaction with methyl acrylate. So number of diene will be 5. In the second question, we can see that we have to identify the major product in this given reaction. Here we can see that OTS is a beta leaving group, and at the trans position or anti orientation there is a double bond, and it will show its neighboring group effect to eliminate this OTS group like this. If we show the mechanism, then in the first step this neighboring pi bond will attack at this carbon OTS sigma star and eliminate this OTS group to form a non-classical carbocation. That is, at a time here will be cation, and here will be bond formation, and similarly it will be in equilibrium. At the second time here will be bond and it will be carbocation, and as a resonance hybrid we can draw the structure like this. It will be positive charge that is distributed between these two carbon, and it is a non-classical carbocation. And in the next step, the acetic acid will attack at this center to break this carbon-carbon bond and to form the B as the major product. And the acetic acid will attack from the same phase in which the OTS group resides in the starting material. So lone pair of OH group in acetic acid will attack here and break this carbon-carbon bond, and there will be formation of double bond at the same position as present in the starting material. And after proton abstraction from the acetic acid, since oxygen will attack here, here will be OH plus, and after deprotonation it will be OAC, and OAC group will reside in the same position, that is, there will be retention of configuration at this reacting center, and B will be the final product of this reaction. When acetic acid attack at this position, the carbon-carbon bond will break, and that will form here double bond by overlapping with the vacant p orbital at this carbocationic center, and result in the pi bond in the final product. This is a question from pericyclic reaction. We have to tell about the condition to bring out this following transformation, and from this transformation we can see that in the starting material these two double bond are in E conformation, and in the final product these two ethyl group are in anti orientation, and this orientation, that is the final product, we can get if we perform the quant-rotatory rotation of this conjugated system. And for the 4n plus 2 pi electron system, since here is involved 6 electron, that means 4n plus 2 pi electron system, quant-rotatory rotation is allowed under photochemical condition. That is, the condition for this following transformation will be photochemical condition, and the rotation will be quant rotation. So we can see that option number D is the correct answer. In this question we have to tell about the final product of this reaction, that is this molecule is treated under thermal condition, and in thermal condition it will undergo 3,3 sigmatopic rearrangement, and that will proceed through a 6-member transition state. If we draw the structure in chair conformation, and since here methyl group is above the plane, so it will be methyl, and in the next carbon atom methyl group is also above the plane, so it will be equatorial. Now it will undergo 3,3 sigmatopic rearrangement. Here will be breaking of this 3,3 carbon-carbon bond, and this pi bond will form here sigma bond. This pi bond will break here and will form here pi bond, and the transition state will look like, since here breaking of this pi bond, so I am writing it like dot, and here is formation of pi bond, the breaking of this sigma bond, and here will be formation of pi bond. There is breaking of this pi bond, and here is formation of a sigma bond. Here is methyl, here is also methyl, and if we draw the final product, then it will be the double bond here will be Z, and another double bond will be E. That means in the final product one double bond will be Z and one double bond will be E. And from the given option we can see in the first option both the two double bonds are E, so this option is not correct. In the second case we can see that both the two double bonds are Z in Z orientation, so it is also not correct. And in the third case one double bond is E and another double bond is Z. This is the correct product for this reaction, for this transformation. So we can see that option number C is the correct answer. If we number the carbon here, that is 1 2 3 1 2 3, here will be 1 2 3, this will be 3 2 1, this is 1 2 3 1 2, and this one is 3. So let's see next question. This is a very easy question. We have to tell about the number of compounds that do not exhibit optical activity at room temperature. That is, we have to identify the optically inactive compounds. For the first case we can see that 4 attached group to the carbon atom are different, so it will be optically active, but we have to identify the optically inactive compound, so this is not correct. The second case we can see that there is 3 consecutive double bond. That means in this system the number of double bonds is odd and it will behave like a ethylene like system. So there will be a molecular plane containing carbon-carbon chain, and therefore it will be optically inactive. And in this case there is no symmetry element, so it will be optically active. In the fourth case, if we draw it in the Fischer projection, if we rotate this molecule along this carbon-carbon bond, then it will be, here will be OH, here will be OH, and CO2H will come this side, and here will be CO2H. And in this molecule there will be a sigma plane cutting this molecule into two half. That is, this will be a meso compound and it will be optically inactive. In this case this biphenyl system, since the hydrogen and fluorine atom are smaller in size, therefore the rotation along this carbon-carbon bond in this biphenyl system will not be restricted, and there will be free rotation along this carbon-carbon bond in this biphenyl system. Therefore, there will be a molecular plane and it will be optically inactive. And similarly, in the last case, there will be a sigma plane passing through this, containing this carbon, this phenyl carbon, this carbon, and this carbon, that will pass containing this 4 carbon atom and will bisect this molecule into 2 equal halves. That means the sigma plane will pass like this, and it will also bisect this below phenyl part into 2 equal halves. Therefore, it will be optically inactive. That means we can see here that this 4 compound will be optically inactive and they will not show optical activity. So number of compounds that do not show optical activity is 4. This is a question from NMR spectroscopy. It is given that in a 400 MHz photon NMR spectrometer, a photon resonates at 1560 Hz higher than that of tetramethylsilane, that is primary standard, and its chemical shift is fixed at 0 ppm. We have to identify or calculate the chemical shift value of this photon which resonates at 1560 Hz higher than that of tetramethylsilane. Now, from the formula of chemical shift, that is chemical shift of a peak or of a photon is equal to frequency of the proton in the photon NMR in Hertz divided by the operating frequency of the instrument in Hertz, that is multiplied by 10 to the 6, and the unit of the chemical shift will be in ppm value. Okay, we can also write this equation like frequency in Hertz of the nucleus for which we are calculating the chemical shift value divided by the operating frequency of the instrument in megahertz. That will come in ppm. That is also chemical shift. And here we need not require to multiply this term with 10 to the 6 since it is given in megahertz. So if you put the value, that is the photon resonates at 1560 Hz and the operating frequency is 400 megahertz, that means 400 into 10 to the 6 Hz into 10 to the power 6. That means the value will come like this, is 3.9. That is the chemical shift value for this photon is 3.9 ppm. It is very simple question. In the next question, we have to identify the final product, major product for this given transformation. And here is we can see that the reagents are tri-N-butyl tin hydride AIBN, that is azo-isobutyronitride, and it is reacting and at thermal condition. At the thermal condition, AIBN under thermal condition will undergo homolytic cleavage to eliminate nitrogen and from the corresponding radical. And in the next step, it will abstract one hydrogen atom from tributyl tin hydride and will generate the corresponding tributyl tin radical, tributyl SN radical. And now this radical can abstract one halogen atom from the given starting material and will form result its corresponding radical. That radical will be here is CO2Me, and here is 1 2 3 4 5 carbon radical. This will be the radical. Now it will undergo homolytic cleavage to form here corresponding acyl radical, and this radical. This radical will be stabilized by the conjugation with this carbonyl group of this A star. Now in the next step there will be a combination of this radical to form such 1 2 3 4 5 6 7 8 9 10 member macrocyclic ring. Now in the next step this radical will abstract one hydrogen atom from this tributyl tin hydride. And will result its corresponding alkane. You can see that option number A is the correct answer for this reaction. Is it okay? You have to be careful that in the last step it will not abstract one halogen atom from the generated species here. That is, since after abstraction of halogen atom from the starting material by this radical, there will be generation of this tin iodine complex, and this species cannot abstract one iodine atom from this tin iodine bond, since this tin iodine bond will be stable enough than that of tin hydrogen bond. So in this step this radical will abstract one hydrogen atom from this tributyl tin hydride instead of iodine atom, and this will be the final product, not this one. Okay, and there will be not also the formation of this olefin, since here is a source of hydrogen atom, so there will be abstraction of hydrogen atom by this radical instead of hydrogen elimination. Okay. In this question we have to tell about the major product forming in this reaction. CO2Me and this is CO2H. Now in the first condition there is given as B2H6, that is diboron, and in presence of diboron acid group gets reduced to alcohol instead of ester. Ester will remain as intact. B2H6, that is diboron, only reduce acid group to its corresponding alcohol. Therefore the generated alcohol will be, here will be CH2OH, here will be hydrogen, and these two groups will remain as intact, and ester group will not be affected by this diboron. And in the next step, in presence of acid, there will be cyclization. Acid will activate this carbonyl group, and in the next step the lone pair of oxygen will attack here, and in the next step there will be elimination of OMe group. This liberated OMe group will abstract one proton from here and from the corresponding lactone, 6-member lactone, and the orientation of the hydrogen and this isopropyl group will remain as it is in the starting material. So you can see that option number B is the correct answer. You have to just keep in mind that diboron will only reduce acid group instead of the ester. Ester will remain as intact. In this question, this two equivalent of beta keto ester, since it is alpha, it is beta keto ester is reacted with formaldehyde in presence of sodium ethoxide base under thermal condition. Now I am drawing the mechanism of this reaction along with I will tell at the final the major product of this reaction. In the first step, since this proton is acidic enough, the base will abstract this acidic proton and will form the corresponding anion. That anion will be stabilized through conjugation with this ester and carbonyl group. This will attack on the formaldehyde here will be, this is the formaldehyde part, CH2OH. In the next step, the base will abstract this acidic proton and will form the corresponding anion. That anion will be stabilized by the conjugation with this carbonyl group. That means there will be formation of enolate. This enolate, it will form here double bond and it will eliminate this OH group. In the next step, since in the reaction medium there is another beta keto ester moiety, it will form the corresponding anion and it will attack at this alpha beta conjugated carbonyl or alpha beta conjugated ester system. This anion will attack here. We will open up this carbonyl group. Okay. In the next step, the anion will form here double bond. It will migrate here and it will abstract H plus from ethanol. Okay. Now this species, in presence of base will abstract one acidic proton from this carbon and will form here corresponding anion. That anion will attack at this carbonyl group to form the cyclic product. Okay. There are under thermal condition, there will be a dehydration and the base will abstract this acidic proton from here anion. That anion will be stabilized through conjugation with this carbonyl group and again back formation of this carbonyl group and liberation of this OH group. That means there will be formation of here double bond. And there is one more important thing, that this is a beta keto ester moiety, and in presence of ethanol, that is it can act as a proton source. Under thermal condition it will first get hydrolyzed to corresponding acid, and since beta keto acid is thermally unstable, under thermal condition it will undergo decarboxylation to form the corresponding decarboxylated product. So the final product will be this one, not this one. You can see that option number D is the correct answer. Is it okay? Okay, let's see next question. You have to tell in this reaction the major product. At the first step, there will be a Grignard reaction and methyl anion will attack at this carbonyl group to form the alcohol. And this is in the second condition is treated under acidic condition. In acidic condition, this OH group will be protonated and there will be ring expansion, elimination of water. So there will be formation of 5-member ring. Here is methyl and this is a here will be generation of carbocation and it is 2-degree carbocation. Since there is a possibility of rearrangement, so in the next step there will be 1,2 hydride shift. And formation of more stable 3-degree carbocation. So this will be 3-degree and more stable. And in the next step the anion counterpart of HCl will attack at this carbocationic center to form this chloroalkane. So option number D is the correct answer, not the C. If you attack the chloride minus here in this 2-degree carbocation, then you will get this product, but this is not the major product. There will be rearrangement 1,2 hydride shift and formation of 3-degree carbocation, and the major product will be given from this carbocation. So this is the final product. This question I will not solve here, since I have already uploaded one video describing or solving few questions related to such coupling reaction. If you have not watched that video, or you can get the answer of this question from that video, I will give the link in the description box. You can check that link, and here you will get the, I am just saying that the final product of this reaction is option number C. This is an important question. We have to tell about the major product for this reaction, and this primary alcohol is treated with PCC, and it is a chromium containing oxidizing agent. In presence of PCC, this primary alcohol will get oxidized to aldehyde, and for the first step the product will be this one. And in the next step, in presence of zinc bromide, it will act as a Lewis acid. It will activate this carbonyl group, and there will be attack of this double bond at this carbonyl center to form 1, 2, 3, 4, 5, 6 member ring. And the main important thing here is the stereochemistry of the different substituent within the cyclic ring. So to show the stereochemistry of the different substituent, I am drawing this structure like this. One, two, three. At 3 position there is methyl, and which is below the plane. This pi electron cloud of this double bond will attack at this carbonyl center. This carbonyl center is coordinated to zinc, that will activate this carbonyl group, that is electrophilicity of this carbonyl carbon. Now this pi electron cloud of this double bond will attack here and open up this carbonyl group. Now the main factor is the side, that is the orientation of the attack of this double bond at this carbonyl carbon. Since the methyl group is below the plane, so attack of this double bond will occur from above the plane, and this carbonyl group, that is after opening of this carbonyl group, the carbon O minus bond will be below the plane, since attack will be from above the plane. So we can write it O minus, and here will be carbocation, and this group will be above the plane. In the next step, this O minus will abstract one acidic proton from this CH bond, and there will be formation of double bond here. So it will be OH, and methyl group here will be as it is from below the plane, and this group will be above the plane. So we can see that option number C is the correct answer. Is it okay? If you feel any difficulty, then you can let me know in the comment section, or you can send me a mail. So let's see next question. Here it is given a allylic ether or allylic alcohol, and it is treated with benzoic acid. That means here the given condition is for epoxidation, and we have to tell about the orientation of the epoxide ring with respect to this OR group. Now if the R is hydrogen, that means if it is OH, then the transfer or epoxidation will occur from the phase in which the OH group resides, and that orientation of the epoxidation will be dictated by the hydrogen bonding of this OH group with the oxygen atom of this per acid. Therefore, the oxygen transfer from this per acid will be from the same phase as that of OH. But if the R is COET, that is this carbonyl group, then since there is no acidic hydrogen atom, therefore there is no chance of hydrogen bonding with the oxygen atom of per acid. Therefore, due to steric effect, the epoxidation will take place from opposite phase as that of OCOET, that is OR. Thus, we can say if R is hydrogen and OH is above the plane, so epoxidation will also take place above the plane. If OH is below the plane, then epoxidation will take place from below the plane. Since in all the cases OH is given from above the plane, so I am writing it above the plane, and therefore the Q will be this product. And if R is COET, that is OCOET, then due to steric effect the epoxidation will occur from opposite phase as that of OR group, and this will be P. Therefore, we can see that option number B is the correct answer. In this question, this alpha beta unsaturated carbonyl compound is treated with Gilman reagent, and a Gilman reagent is a source of methyl minus, and that is a source of soft nucleophile methyl anion, and therefore the methyl anion will attack in 1,4 orientation with respect to this carbonyl group. And if the methyl anion will attacks here, then there will be formation of double bond. Here will be opening of this carbon oxygen double bond, and there will be generation of O minus. When this anion will form the back carbon oxygen pi bond, there will be anion, and that anion will attack this electrophile in the second step. Here anion will attack here, and selenium bromide bond will break. Now the question is the stereochemistry of the second incoming group. Now if the methyl group attacks from below the plane, then the second electrophile will orient in the opposite direction as that of first nucleophile. That is, the orientation of these two vicinal group will be opposite, that is anti. Though in the given options there is no confusion with the stereochemistry, so the first product P will be this one. In the second step, in the oxidizing condition, H2O2 will oxidize this selenium center, and it will form selenium oxide bond. Here will be selenium plus O minus, that is methyl. I am writing it considering the stereochemistry of the selenium center and methyl center. It will help you to understand it in better way. Now in the next step, since here is one hydrogen that is above the plane, it will abstract this hydrogen atom from here double bond, and this carbon selenium bond will break. Therefore there will be formation of double bond and generation of this 1 2 3 methyl alpha beta unsaturated cyclohexenone. Therefore the Q will be this one. So option number B is the correct answer. Is it okay? You can see here that the orientation of this methyl and this selenium group must be anti, since after oxidation, if this methyl and selenium center is not anti, there it will not get any hydrogen atom in the same phase as that of selenium group to eliminate or to abstract and to form this double bond. Is it clear? Okay. This is the last question for this discussion, and we have to tell the major product in this reaction. In the first step, oxide minus will attack on the acetic anhydride carbonyl center of acetic anhydride, and we will eliminate this OAC minus group. This will generate this product, and in the next step the liberated OAC minus will abstract this acidic proton, and we will form here double bond, and this carbon nitrogen bond will break. Okay, the next step there will be rearrangement, and that will be there will be breaking of this nitrogen oxygen bond, and will form here double bond. This carbon oxygen bond will break, from here anion, that anion will attack at this carbon carbon double bond, will form here double bond. Is it clear? Therefore here will be OCO methyl. This will be the final product. If we draw it in clear way, that is, it will be OAC, OCO-Me. Therefore we can see that option number C is the correct answer of this reaction. This will be the major product. Is it okay? So that's all for this discussion. If you like this video, you can share it with your friends, and if you are new in this channel, then you can subscribe to my channel Chem Analysis to get such interesting videos in future. Thank you.